Now we're done talking about displacement, velocity, and acceleration. It is time to learn a tool that helps you describe the motion in a more precise terms. Today we will talk about vectors and how to describe motion using vectors, how to analyze vectors, how to plug in the vectors on the Cartesian, and how to solve all related problems that need vectors to be used in order to find the final solution. So vectors basically are used to describe motion. Let's see here we have a rocket. This rocket is launching in a linear line upwards. You want to be able to describe the motion of this rocket. Usually we use vectors to describe the motion in magnitude and direction. Anything doing a certain motion with magnitude and direction need a vector to describe it. So we can describe the displacement using vectors, velocity and acceleration, but the difference here, you can describe the motion in more details and being able to analyze and solve more complicated motions in terms of vector analysis. So here we have a rocket. This rocket is going as an arrow that is going upwards. This arrow have a start point and an end point. The start point, we call it a tail. End point, we call it the head of that arrow. And this arrow have a magnitude and it has a direction that is going up. So let's learn more in details about the vectors basics. So the simplest form of vector looking like this, there is an arrow going in a certain direction. The arrow has a tail and a head and it has a magnitude of A. Mathematically, we represent any vector that has a magnitude and direction with an arrow above that letter or that value. So in this case, we know A is a directional vector and it has a magnitude and a direction in the same time. For vectors, many cases, like you have an object that's moving east for a certain amount of time or for a certain magnitude, then it's going west, or let's say it's going north for a certain magnitude, then you want to be able to add those vectors and find the sum, or what we call as the resultant of that vector, or the resultant of motion. Again, the motion could be displacement, could be velocity, could be acceleration, could be force. Any kind of value that is having a magnitude and a direction can be represented in terms of vectors. So in this case, we have vector A going in this direction. It's not exactly east. It's going in a kind of diagonal motion in this case. We will talk in details more on how to represent this kind of motion in more details. Then at the head of the first vector, you have the tail of the second vector, which is B. Now to find the total motion or total displacement of vectors A and B, we connect the first tail to the last head of those connected or consecutive vectors. And in this case, vector C representing the total motion that happened by going through vector A and vector B. And this what we call here the sum or the resultant. Mathematically, C equals the magnitude of A plus the magnitude of B. So as you can see, C equals A plus B. We call C in this case the resultant or the sum of the vector motion, and in this case we're adding vectors, and obviously it's called a sum because you are summing the magnitudes of all the vectors involved in this kind of category. Now let's have an example on adding vectors. We have a snow show race moving forward 10 meters and he need through the game rules to untie a series of knots, then move forward again for 5 meters, then solve a puzzle, then move finally forward 25 meters until he reached the finish line, as we can see in this figure. And in this case, the question is telling us to determine the resultant vector by adding the vectors graphically. So you will go in details of the question and you start to add the arrows one by one, and you find the resultant vector that's connecting the tail of the first vector to the head of the last vector graphically. So let's draw what we're given already. We're given that the player is moving 10 meters forward. So he moved and he stopped here. Then he moved 5 meters forward as well. So here we're talking only on one direction. So there's no confusion here. So you're going to the side or to the right or to the right hand side of the x-axis. So he moved 10 meters, then he stopped, then he moved 5 meters, then eventually he moved 25 meters. Now he say find the resultant vector. Resultant vector will be from the tail of the first vector to the head of the last vector in the same direction, in this case. So we can draw a straight line that goes from the first tail to the last tip, and that would be your resultant. What is the value of that resultant? It is the summation of all the values that we can see graphically over here. So 10 plus 5 plus 25, that's 50 meters to the right or 50 meters forward. Now, of course, as we're adding vectors, we are subtracting vectors as well. So in this case, same example we used before, we have vector A, we have vector B, and we have vector C as the resultant of A and B. Now, what if we want to find B? B would equal C minus A. How we know that? Remember, when we found C as the resultant of A and B, it was C equals A plus B. And if you simplify the equation a little more, you move B to the left and you move C to the right. We'll change its sign. In this case, B equals C minus A. Let's take a subtracting vectors example. We have a sailboat. Initially, he was 15 meters to the right of the origin, and it moved with time 35 meters to the left. We need to determine the sailboat displacement, how much he moved from here to here, algebraically by numbers and graphically. So what we have the initial distance or displacement equals 15 meters to the right, assuming the right as a positive. And the D final is 35 meters to the left, that's minus 35 meters. It's good to mention that we have now above our variables, we have an arrow that is saying it's a directional value over here. So that's what's given. What is required? We need the delta D in this case. How to find delta D? Algebraically, delta D is D final minus D initial, as you remember in the displacement equation that we had before. D final minus 35 as a given, minus the plus 15 meters that was initial displacement. So it will be eventually minus 35 minus 15 will give you minus 50 meter, and negative means the direction is to the left. The second part of the question, solve that graphically. So graphically we have D initial go this way, D final go this way. We need to find delta D. It goes from here all the way to here. So to solve the problem graphically, in many questions you should have a scale, like there should be a grading over here to be able to use your ruler and make sure that things to scale. In this case, we need to do 1 centimeter equals 10 meters. So we measure with the ruler and we have a gradient over here. The distance between here and here was 5 centimeters, but since the scale, each 1 centimeter equals 10 meters, that would end up being 50 meters to the left.